So first we would like to invite Leonel. Okay, Leonel is director of the Unidad Avanzada de Bioimagenología at the Instituto Pasteur at Montevideo, Uruguay, and his work is focused on film microscopy and hyperspectral imaging. Welcome, Leonel.
Well, thank you very much. It's my pleasure to be in another LABI meeting. And today I'm going to talk about a technology that we have been developing for the past couple of years in Uruguay, the diver microscope. Okay. Okay, so basically this technology is aiming for deep tissue imaging and working in live samples. And basically, as Nicole said, I am the head of the Advanced Bioimaging Unit. This is a joint initiative between the Instituto Pasteur and the Universidad de la República at the Clinical Hospital in Montevideo, with the main goal of fulfill these four claims that we have here: provide services, train dissemination, developing technology in terms of hardware, software, and methods, blending spectroscopy and microscopy, and basically use this technology for biological question in the lab. So speaking about technology, we have several commercial microscopes with the new 990 that we just received, but we also develop other technologies that we either adopt or we basically develop in our place. And we also have capabilities for bioimaging processing with several high performance workstation and also computing and storage server for the technologies that produce a massive amount of data. So speaking about multiphoton microscopy and deep tissue imaging, one of the issues even for multiphoton microscopy is when you want to go very deep in the tissue, you have to pump your laser. As higher you pump your laser, you start to have autofluorescence due to the high rate of light that you are applying, and this basically goes contrary to the penetration. The reason for why this happens is because, well, you have a wavefront distortion due to the travel of light through the tissue, and basically the inhomogeneity in the index of refraction will make your sample very, very clean and crispy at the beginning and in C, but when you go deep, 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 basically you start to blur your image. So the diamond microscope is a technology that aims to catch more and more photon in comparison with any two-photon epi-detection microscope. But before going to the diver, I want to mention that there are several other alternatives in the business that use either this parabolic mirror or fiber optics surrounding to the cone of illumination and detection in epi-detection in order to increase the number of photons you can collect. And even in the best situation, you can go 2 to 5 folds gain in number of photons in comparison to the epi-detection. The other possibility is always to clarify your tissue, but for most of the application that we run in our lab, we don't want to clarify samples. We want to work with samples in the native state. So for that reason, many years ago, Enrico Graton, Sasha Dvornikova, and Viera Kerstingari developed this technology. In a regular epi-detection microscope, we have an excitation, and basically the optic focalizes the light into the tissue, and the two-photon spots emit in all directions. Within the tissue, with high scattering, you have photons that undergoes in all directions, and you have only a small angle to collect the photon that you excite. Well, the diver is a very simple concept. So basically, it's a microscope that has a detector in forward, a very large area. This is a 1-inch square detector that collects photons under scattered. And the reason for why it can collect photons in scattered regime that you cannot collect in the epi-detection is because you have a much index of refraction and there is no optic in between. So basically, it's like a transparent path for photons arriving to the detector. So we can collect virtual numerical aperture than any other epi-detection can do. And this is an example. If you match index of refraction between slices with water, you can see through the slices, and if you don't, basically the photons get scattered. So in overall, basically, you can go up to 1,000 times more signal to noise in comparison to any two-photon microscope. So this is the detector. Basically, what you need to do is to build a detector. And the detector is basically a wheel embedded in ethylene glycol with glass filters. And this is the Hamamatsu detector. It's a PMT that we use. It's compatible with custom, but also with commercial microscope. So there is only 4 microscopes, all built by Sasha Dvornikov in US. And the 5th is the diver in Montevideo, Uruguay, which is the only one outside in the world. And basically, this technology requires you to build basically all the mechanics in order to put together a microscope that looks like this. And this is the software performing and scanning, in a piece of sample for calibration purposes. So what are the benefits of this technology? Well, one of the big benefits of this technology is the enormous or giant field of view. So you can go to samples that are centimeter long. And the reason for why is because we have a scanning optic of 2 inches, so we can really steer, the beam widely than any other commercial microscope. We can also go deep, and the reason for why we go deep is because this wide detection, and basically in a very high scattering condition, like in a phantom here, we can go up 2 millimeter, basically 600-fold time increase in sensitivity in comparison to EP detection. But we cannot even be sensitive in a transparent sample. And the reason for why is very simple. As deeper you go, the virtual numerical aperture you have is increased because you are collecting photons that are emitting closer and closer to the detector. So virtually, you have different excitation and emission numerical aperture. And this is the reason for why we can go deeper and deeper. So the applications, basically, we stress the use of this technology in combination with fluorescent lifetime imaging microscopy. And the reason for why is because we wanted to use for label-free metabolic imaging. And NADH is a metabolite that we have in all our cells. And basically, it can be in 2 forms within the cell, free and bound to the enzyme that this cofactor does, a job in the cell. And basically, using this measurement, we can measure the heterogeneity lifetime as a metabolic index of the cells. And using that, for instance, we can see in slices of rat lung, basically the metabolism between, a lung that undergoes to damage by bronchoalveolar lavage. So basically, we can use this for metabolic imaging in cells and also in tissue. The other very 2 strong applications are also in level 3 for second harmonic generation. Second harmonic generation is a signal that propagates in forward in a structure with not centrosymmetric structures like collagen and myosin, or and is very strong in urea crystal. And basically, we can use this for studying fibrosis in kidney or separate the different collagen in the femur that I showed before. In the intensity image. But now, basically, regarding to the information of the lifetime and the second harmonic generation that different collagen generates. The other thing that is very strong is for third harmonic generation, and in that case, the signal is generated basically in changes, in dramatic changes and index of refraction, and this happens, for instance, at the surface of lipid droplets, and this is an example that we did long time in the lab, where basically we can see in a liver the effect of high-fat diet and the accumulation of very large lipid droplet in the adipocytes. But also can be used for 3D imaging of sciatic nerve, combining third harmonic generation, second harmonic generation, and autofluorescence. The last thing that I want to mention is this microscope is also compatible with the hyperspectral imaging. And basically, in hyperspectral imaging, we need to collect step by step the different wavelength to recompose the spectra. And then we use this in the spectral phasor analysis, which is a Fourier transformation of the hyperspectral data. But Enrico came up with an idea like 6-5 years ago, in which if we collect the data in a modulated spectra, basically we can do the phasor transformation on the optics, but not in the using mathematics. And doing so, we can also acquire information from the same femur. And basically, here is the different spectra from collagen regarding to lifetime, and this is information regarding to the spectra that the collagen information give you. So it's also a very nice characteristic of the diver that is not easy to achieve with regular hyperspectral imaging in confocal microscopy, because scatter photon doesn't go well with dispersive optics. The final thing is the microscope is compatible with adaptive optics, and in the Enrico's lab, they also implemented adaptive optics in order to increase even further the capabilities of deep. And to finalize in my last 30 seconds, I want to thank the team that was putting together the diver, Luis Inchausti, Micaela Lopacio, Sasha Dvornikov, who was in the lab, and also collaborators over the year. In particular, I want to mention Enrico Granton, who was my former postdoc mentor and also a big inspiration for what we do at the Advanced Bioimaging Unit in Uruguay. I want to finish wrapping up saying that we are pushing in other directions. So we received a new heart for the diver. This is a new laser with an extended range that we wanted to use for purposes of exciting other molecules, but also for other spectroscopy like Webeland mixing, cars, and things like that. We are waiting for our Flamingo, which is a fantastic initiative between Uruguay, Brazil, and Chile. And there are many friends here participating in the consortium. We are also working on the image scanning microscopy in collaboration with Giuseppe Vicidomiti in combination with FLIM. And we have implemented phasor pi and a pariphasor for all the analysis of fluorescent lifetime hyperspectral imaging. With that, I want to thank the funders, and of course, I want to thank my team, which basically the people who does all the heavy work in the lab. Thank you.
Thank you, Leonel. Our next speaker is Rupert Ecker. Rupert is CEO of TissueGnostics, which you probably saw in the hall during the coffee break. And he's also adjunct professor at Queensland University of Technology in Australia. So please welcome Rupert.
Yeah, thank you very much for the kind introduction. It's my great pleasure to be here today in Buenos Aires and talk about my passion. My passion being bringing the idea of flow cytometry, which is quantitative analysis of antibody-mediated staining on the level of individual cells, bringing this idea from cell suspensions. Thank you. From cell suspensions to the tissue section, the microscopic slide. And I have been working on this passion both academically. I'm a cell biologist by training and developed a prototype of this technology for tissue image cytometry as part of my PhD thesis in the 1990s. Founded a company, TissueGnostics, and then came back to academia, and now I'm working at Queensland University of Technology in Brisbane. And when we started, I made a search by the time, it was 2003 when the company was founded, on PubMed and looked for fax or flow cytometry. And I found thousands of papers which had used flow cytometry as a tool of research and discovery. And there was not one which used tissue image cytometry. I'm not going to talk about our products. If you're interested, then please see me and my team outside at the booth, but I would like to draw a more comprehensive overview and also reflect on the basics. Probably because we are here in a bioimaging community, many of you will know this image. So the core question is about perception. And if you look on these two frames, A and B, we will probably all agree that A looks much better, much darker than B, but in fact it's not. A and B have the same gray value. It's an optical illusion that makes us believe A is darker than B. And this is something we have to be aware of, that if this was a tissue section with a cell stained for whatever marker you're interested in, we would see here a cell in a high background environment and conclude its marker negative, but here we would see a cell in a low background environment and conclude its marker positive, and we would be wrong. So the take-home message of this slide is that our perception might not be determined by the structure of interest we are looking at, but by its vicinity, their surrounding. It also comes true when it's counting of cells. We see here classical immunohistochemistry staining with a well-known marker, Ki67, proliferation marker in brown, peroxidase. And the obvious question is how many cells are proliferating, or how many of the blue nuclei are also brown. We made a survey among more than 300 scientists, and believe it or not, the answers that we received ranged from 0.5 to 60%. These were all scientists. I'm not talking about people on the street. And I think this is a significant difference, and it shows the main problem associated with visual evaluation. It not only depends on whom you ask, but also when you ask. If the person is if it's in the morning, or if someone is tired, if you sit in a dark room like microscopists often do, or if the sun is shining through the window, all this might change your judgment. And as TissueGnostics, we are offering software to introduce observer independence in the analysis of these slides, and also academically I'm working, I will show this in the next slide, on algorithms for next generation histopathology. But we have to always keep in mind that software can do a lot, like increase the contrast, remove the background, make spectral unmixing and so on. But the basic is always our experiment. And if the experiment doesn't work, don't expect the software can give you good data. And in that sense, I would like to point to this paper, which was published almost a year ago, almost on a day a year ago, where the authors analyzed 16 commercially antibodies for a specific protein. Doesn't matter now which protein that is. The point is, these are antibodies, and they checked and found that of those 16 commercially available antibodies, only 3 performed well, meaning specifically bound the target protein and without cross-reaction. And there were no papers published on that protein using these 3 antibodies. And now, fasten your seatbelt. But not one published study has used those. About 15 papers described experiments using an antibody that didn't even bind the key protein. And these 15 papers were cited, collectively cited more than 3,000 times. Whew. So this is the background on which I have been working over the past almost 30 years, including my PhD thesis. And as I said, I have a commercial leg, which is the company TissueGnostics. Feel free to visit us outside at the booth if you want to know about the products. But also still an academic leg. I'm working at Queensland University of Technology, and here we are specifically working on a project that is called the Virtual Histopathologist for Precision Cancer Diagnostics. This is mainly development of deep learning algorithms for analysis of histological samples. Just a word about QUT, a little bit of advertisement for my university and for Australia. It's based in the wonderful city of Brisbane in Queensland, and it's doing pretty well in the international ranking. I belong to the Faculty of Health, School of Biomedical Science. I'm physically based at the wonderful institute or building. It's the Translational Research Institute of Australia, where QUT, University of Queensland and Mater Research, Mater is a private hospital chain in Australia, collaborate on realizing translational research aspects. And QUT will also start a School of Medicine in 2028. So if any students are around and would be interested to come to Australia, think of QUT, please. The company TissueGnostics, which I co-founded in 2003, is located in the city of Vienna in Austria. So to be clear, there are no kangaroos in Austria, okay? But they are in Australia. And we are still located in this beautiful building close to the city center. But today we have a global network of subsidiaries. Like outside at the booth is my colleague Bogdan from TissueGnostics Romania. Here is my colleague Felipe from TissueGnostics Latam division. Please reach out. And in order to achieve this goal of bringing the idea of flow cytometry with state-of-the-art algorithms to the microscopic slide, we have been collaborating with academic partners, not only in Australia in form of QUT, where I am based, but also in Europe. And I would like to mention these 7 consortia. Maybe you have heard of the Marie Curie Innovative Training Networks. This is a funding scheme from the European Union, where there are always several universities from Europe and industry partners like TissueGnostics come together to work on a specific project. And the EU funds each of these projects with typically 3 to 6 million euro. And the projects to which we participated so far were EIDPath, which looked into computational pathology, INSEM with Technical University Aachen, where we looked on cell migration studies, Alcatraz, looking on the anaplastic lymphoma kinase as a project in translational oncology, with University of Cambridge, the calcium sensing receptor network, Helical with Trinity College in Dublin, big data analysis by machine learning. These 5 projects already finished. Ongoing are these 2, SSBB with the Erasmus Medical Center in Rotterdam in the Netherlands on the increasing problem of multi-drug resistance in bacteria, and Eradicate with Medical University Vienna on stem cells and cancer stem cells. So with the instruments and technology we develop partially in these academic research groups and then come into the commercial software, we can offer observer independent analysis like of this sample, which then shows us that here there are 15.8% of the cells. Each dot here represents a single cell, and you can create gates like you know it from flow cytometry. We can also look into spatial analysis. The term spatial biology is nowadays very popular. I would like to mention that we already did spatial biology 15 years ago. We didn't call it spatial biology, we called it contextual tissue cytometry. And with this I would like to summarize. As of end of last month, we have 3,450 peer-reviewed publications. You see from where in the world they come. And here you see how the increases of papers per year published using tissue image cytometry. This shows which fields are used. Number 1 is actually cancer research, followed by neuroscience and immunology, but it can be applied in all disciplines of science. And with this I would like to acknowledge the contribution of our academic partners in Europe, in Australia. I would also like to mention at USP in Sao Paulo we have Professor Henning Ulrich, one of our scientific advisors, and Karen Jacobs. And this relates actually to the panel discussion we had before the coffee break. And I don't have the time to go in detail, but I encourage you to look into the Africa Microscopy Initiative, which is an initiative funded by the Zuckerberg Foundation and Bill Gates Foundation, and they offer high-end imaging equipment to researchers all over Africa. And I think this could be a very good model also for Latin America. With this, thank you very much for your attention. Please visit us at our booth, I don't know, is there, and feel free to reach out to me on LinkedIn. Thank you very much.
Thank you, Rupert. So our next speaker is Emiliano Medei. Emiliano works at the Instituto de Biofísica Carlos Chagas in Universidad Federal de Rio de Janeiro, Brazil. And today he will tell us about his work at the Bioimaging multi-user unit in Senabio. So let's welcome Emiliano with a round of applause.
¿Aló? ¿Puedo hablar acá? ¿Puedo hablar en este? Sí. Okay. Thank you so much for the invitation, and it's a really honor to be here. And I'll be really honest for you that my heart is beating fast now, and so emotional for me because I was a student here in the University of Buenos Aires when I started my MD, just 2 blocks here in the CBC, so en el CBC, acá en la ciudad universitaria. So, and it's not easy for me to back home after more than 20 years out of Argentina working in Brazil. So thank you so much for the invitation, and it's really a pleasure to be here. And thank you to Fernanda Moll for inviting me, and Kildare, our director of our institute, also for this beautiful meeting. So I will introduce you about our National Center of Bioimaging. So that is places in the Federal University of Rio de Janeiro. So the concept of this building was to put together not only a lot of equipment, but it's put to some mentality, how to study from the molecule, from the structure to the molecule, and the bioimaging from whole animals. So to do or to perform of this kind of roadmap, and not only for drug discovery, but also for investigate different disease or physiopathology disease or basic research only. And we have first one structural biology unit with several NMR spectrometers, and the last one was this 900 spectrometers, and all of these are working on 7/24 every day, and are open for all people around Brazil, but not only Brazil, and from South America. Several people came to Rio de Janeiro to use this kind of equipment. So, and the next step is to understand that, as I told you, the most important is not only to have the equipment, the people, the persons that are working in these facilities. And since 2012, we have the honor to invite Kurt Wittrich, who was a Nobel laureate in chemistry in 2002, and he started to collaborate with us in the Sena Bio, and this was really interesting because not only visit the unit and the facility, but also he was advisor of the postdoctoral fellowship, and he was incorporated in our postgraduate program. And the second unit is the microscopy, obviously, that Kildare here is the most indicated people to talk about the microscopy. Here is the authority in microscopy in our unit, and now under the direction of Marcia Tia, who is here also. This unit have several microscopes, and you know much more like me in microscopy, but as you can see, you have some light microscopies, and also the optical tracer and is just working and installing, and different other microscopy for structure and cell and tissue. And in electronic microscopy, we have a large number also of microscopy. We want to highlight these two microscopy. First, the super resolution that is well working in our facility also. And this Auriga also that was published years ago, this beautiful image reconstruction in our facility. So again, it's important, I will remark again, the people that work in there, and we have a core of technologists and technicians that not only help with the machine, but also to think and help to the guy that need, the investigator that need to perform the experiment, which kind of technique is better for you to use at the time of the experiment. I think that this is the advantage that you have. So, and where we are going. So now was a dream years ago, but now it's not more a dream. Now it's really, and our unit have these both and cutting-edge machines working, and not only working, but I want to highlight the content of Kildare, Marcia, and all unit of microscopy, because not only install the equipment, but also given given different training, hand-on training, and not only for Brazil, but also for South America and from the region. So this is really important for us, and to create this atmosphere that facilitate this kind of advance in this technique. And finally, but not less important, the third facility is for small animals. So do you remember we start in structural molecules, after to cells and tissue, and now, and the third building, all of them are in the really, really close one of the other, okay? So I am talking about 2,000 square meters one to the other, so no more than 100 meters. So in this one, we have we are able to study from the isolated organ to the whole animals. The isolated organs is, I put something that maybe could be interesting, that is hosted just in my lab now, but we are working with this system. This is a homemade system, performing some friend that I will talk about. And we are able, with the local field fluorescent microscopy, we are able by load the heart with a fluorophore, and we are able to perform this recording of the cardiac action potentials and cardiac and calcium transient simultaneously, really, really close places. It was possible by Ariel Escobar, that was a professor in UC Merced, and Ariel was in biophysics, and I can talk so because he passed away this last December, and Ariel was like a brother for me, like a big father for me, and he was the guy, you know, who has the lucky to know him, and he know, and so it allows us to publish different works with this technique, and this year we were very lucky to put this in the cover of the Nature Cardiovascular Research. So regarding the small animals, it's important to highlight this machine that is an MRI, PET MRI, and 7 Tesla. This is both together. We have just the upgrade this year that is allow us not only to perform the anatomical places, but also to overlap and to identify where we have the function, the cardiac function, or at least the cardiac metabolic function that is possible to record with the PET. So with this MRI, as I told you, this is a multi-user and center. So with this machine, we do not only make an preclinical science, but also, and you can see, we have for biology different animals, and we were able to study in depth different structure. We have an in vivo also Ibis lumina. We have a luciferase system, for example, with a trypanostic, and this is important for Chagas disease, for example, but several other fluorescent or luminescent molecules could be used in this system. And echocardiography for different structure also. And the most important is the translational. We have a partnership with the IDOR Institute of Research and teaching that allow us to perform this translational research between the SenaBio and human also. And finally, but not less important, also we want to show you that we have a strong spread science program in our SenaBio. This is really important for us to integrate the community with our center, not only at the SenaBio, but also outside. We have a big program about 200 kilometers from our university. We bring all of the several equipment, and we perform echocardiography with the students, with the public students. We perform a satellite video, and sometimes the guys from microscopy have the electronic microscopy recording online, and the guys in the school are really, really crazy. Wow, I don't believe that I can see just how you acquire and biological imaging. That is impossible for me in this region. Imagine to see in this region. And so the last initiative of our center, that is one of the most important partners, is the postgraduate program. It's a professional postgraduate program to training the new generation of master and PhD students in bioimaging. This is a beautiful initiative, and also Kildare, Marcia, they have a strong responsibility in this project that is ongoing now. So finally, this is our team, our director, Professor Adalberto Vieira, who is the director of our center, and all of the collaborators and professors that are working in this center. Thank you so much for the attention.
Thank you very much. Hello, hello. Thank you very much, Emiliano. And our last speaker for this session is Fernanda Tovar-Moll. Fernanda is the CEO of the DOR Institute of Research and Education in Brazil, and she will tell us about imaging in clinical and translational research at the DOR Institute. Welcome, Fernanda.
So thank you so much. I'd like to, first of all, thank you, Kildare, to thank a lot Leah and also Oliver and Kildare for the kind invitation, and also for the partnerships that we probably want to even strengthen more now. So maybe I will talk a little bit about the continuation of what Emiliano said. I will try to show a little bit the work that we have been doing at IDOR, and try to give an overview of actually opportunities for collaboration in human research as well. So DOR Institute for Research and Education, it's a not-for-profit research institute that we created 15 years ago in Brazil. It started in Rio de Janeiro, but now we are in different states. It's linked to a hospital network, not only hospitals, but also clinical outpatients units in Brazil, around 80 hospitals now, 79 actually, spread through these different states. And we at IDOR are responsible for research and education integrated with this hospital network. We do have labs in Rio de Janeiro and São Paulo and Bahia, and I will show a little bit how we work. But the data can be collected anywhere. Everywhere we have this dot spot here, we have actually, for example, clinical trials going on in the different states. Those are our numbers. I will not go into detail. We have around 100 researchers working in basic and also clinic research. We do have a grad program and also a master program. So, and also postdoc opportunities. We do have a lot of students here, so maybe in the website you can find some opportunities. And we covered pretty much the majority of the areas of the field in science in terms of healthcare or medicine, but a lot of translational research. So a lot of things that probably can be in common or can be opportunities for collaboration with all of you. Of course, we all fight for funding, not only in the Brazilian agencies, but also we do have some funding that comes from abroad, Brazil as well. We do have a lot of collaborations, a lot of strange collaboration with the Federal University of Rio de Janeiro, Fiocruz, USP, but also with other universities in Europe and also in Europe. And we should and we must collaborate more with Latin America. So this is something that we really need to do. So we do have publications with more than 1,000 institutions. And if we can see here, the majority in the global north. So we need, and it's one of the reasons that we are here collaborating with LABI and also with Bridge. So this is a Wellcome Trust actually project that I'm honored to be part of that together with other researchers. And then we are going to be talking about that tomorrow in different sites. But the main purpose of Bridge is actually to talk about data governance and also collaboration and data sharing. And I think you're going to have the opportunity to hear from us in different. Ivane is going to present, and also we have a poster presented out there. At IDOR, we have also an Agents for Innovation, where we we do some collaborations with startups, and also to also foster the science entrepreneurship as well. We don't have only one lab for each researchers. We work with platforms and all integrated. And I will try to show a little bit about what we have at IDOR. So in Rio, for example, our lab is works a lot with stem cells. And here, as you can see, these are mini brains produced from the urine of patients. And they do a lot of experiments, not only neurons, but also cardiomyocytes and other things. Here in São Paulo, we do have a molecular and cellular biology lab that's all open for different researchers around Brazil and, of course, Latin America. We do have also a molecular pathology lab with all those equipments that probably you are familiar. This is one that's actually is a nanostream. So because we have a lot of patients and samples, so this is one example of the researchers that the biologists are doing with the pathologists in the lab as well. In Rio, we have a lab for samples, so a lot of fluid analysis, including a Simoa, where we are also validating in different with different cohorts, let's say. In the Northeast, in Salvador, we do have a lab that's more specialized in advanced cell therapy. So they do like CAR T cells, they do clinical trials phase 1, and they are accredited by the JC committee. So it's the European accreditation for advanced cell or advanced therapy over there. And for example, Bruno Solano just came back from Jennifer's Downer lab at IGI. We have a partnership with her, with the lab actually. And Bruno is starting the first clinical trial, phase 1 in CRISPR for sickle cell anemia, developed by him and by Ross, that's from Jennifer's lab. And we are starting that in Salvador. So made in Brazil, that one. For clinical trials, we do a lot of clinical trials and actually run in different states. So nowadays we have around 275 clinical trials going on. And starting at the majority, Latin America is the majority of the trials are like phase 2 or 3. We lack actually possibilities of phase 1, but it's starting to change. And we do have around 20 clinical trials phase 1. With the COVID, a lot of vaccine trials, of course, and based on these clinical trials and clinical research, not only commercial, but also non-commercial trials that are run by our researchers, we do also have a biobank. So the biobank from tissues and also from samples helps us a lot with different researchers. These are the main sponsors for commercial clinical trials. And of course, that's the majority of them. They help us to actually receive fundings to really help with their non-commercial clinical trials. But we are very happy when we can do things like that and have the publications like in New England journals. And we always say is that our dream is to have Latin American in the first and the last authorships of all those trials. So talking about imaging, we do have an imaging platform. We have around 90 MRIs. It's 3 Tesla MRI and others 1.5. All those data is integrated, so we can actually collect all those data and analyze together. Even Abramati is the guy that's responsible for this unit at IDOR. And we do perform around 81,000 MRIs per month. So, so that's a huge amount of data that's integrated, can actually help us to run different protocols and also different research questions. So this is just an example of our unit in Rio. From the unit in Rio, even they can access the data that has been collected in the Northeast, for example. And there also we have a neuromodulation unit. And of course, post-processing and software development, those are things that we have been working a couple of years in neuro and now also in other fields using AI. Rosana Rodrigues will show this tomorrow in another panel. And this is just an example of how things work. So, of course, MRI is a huge piece, and I am a radiologist, so I think that's a very important piece here. But imaging without the clinical data, without the samples, without those things integrated, we cannot actually answer any question. So here's just an example of cohorts that we have been running. So we do have samples, we do have a PET, we can do a tracking, we have the clinical data, and of course we have imaging in different here, so Alzheimer's, multiple sclerosis, and others. Just an example, so we just validated, because we had this cohort before from studying dementia, we could validate the first sample of the first test for p-tau in the blood of patients, available for research and also is available already for the patients over there. And also, here just an example, we have been working with quantitative neuroimaging. This is actually my field, so I work with brain connectivity, and we apply those techniques to understand brain development and also neurodegeneration to different disorders, and even applying to things that just arrived. So these are just an example of brain. You all know about long COVID, and long COVID, we studied this too. So those are areas that you have changed in the white matter of patients that actually develop memory impairment, executive impairment, and we see those as well. Just to finish, so this is something that we have been trying to do at IDOR. We tried to do translational and clinical integration, let's say. We did that. This is an example with the Zika virus. So we studied the brain of the kids. We also, Stevens was the first one that actually showed that the neuron was infected by the virus at our lab in Rio. Fernando Boss and others studied the virus and in the genetics. And this integration is possible because we have partnerships with a lot of people, including Senabia. So just to close what Emiliano just said, I was also very lucky to be there during 10 years together with Emiliano and Kildare at the UFRJ. I'm not a professor there anymore, but I'm still a collaborator over there. And we have been trying to do that. So those are patients with callosal degenesis. We discovered a path that's an alternative path in humans, but we had to prove that in animals. So this is mice image showing the same path that we proved to be there, because we also did microscopy in the other unit. So thanks a lot. That's what I was trying to just show a little bit. And actually the main message is to call you all to collaborate more in Latin America. We can do big things together. Thank you so much for the attention.
Thank you. Thank you, Fernanda. And now we thank, of course, all the speakers for the great presentations, and we invite them up here to the stage for our 10 minutes questions. So we will take the questions from the audience, both from the auditorium as well as from our online attendees. Thank you very much. Questions from the audience?
Hi. Well, thank you for everybody for their presentations. I wanted to ask Rupert if it's available, the list of antibodies that you have been able to troubleshoot and validate it for these things, because there are many initiatives, and sometimes it will be good that all these efforts are put together to be available for everybody. Thank you.
So obviously that paper was not from our group, I'm just citing it. Indeed, we do get feedback from clients, and we are about to build a list of antibodies from different vendors where we get confirmation from our users that they work together with our instrument. But this list is in preparation. It's not ready yet.
I was in the SBBF in Brazil a couple of weeks ago, and there was a similar effort also there that was mentioned. It's a huge effort.
It is.
It has to be a joint effort.
Yeah, there are several actually groups or papers who are trying to do a standardization of antibodies. And as I said, I'm a cell biologist by training. I spent my first year of my PhD with a set of antibodies which didn't work actually. Yeah. And we tried to develop enormous complicated protocols with RNase inhibitors and whatsoever, where the staining took a week until all the antibodies were gone. Then my boss said, "Now buy another batch, we try once more," and it worked instantly. Yeah. So I know this from my own experience and history.
Thank you. Another question from the audience? I have a question for mainly for the directors of the facilities, which is if you do have programs or grant-like tools to allow the access of the equipment that you manage with no fee, for example, or that allows mostly early career researchers to access your technologies?
Yeah. So we do have we do help also the design of the experiments, and also we do have the cost, of course. Sometimes it's just not fee, but also just, for example, insumes. Samples, but we do have it's open, and just usually you access another researcher, then you can apply for the use of the equipment. But we do have also some grants for young investigators that are also in our web page, not only from Rio or they don't need to be actually linked to our institution. They can be from different anywhere, and they just we just received 15 grantees from a program called Ciência Pioneira. So you can also look to that.
we are a very small, center, but still, lucky to the grant that we got from Chan Zuckerberg, we have the chance to offer a round of 20 fellowships for we call first experience with advanced bioimaging tools. And the purpose of that grants were for a visit of 10 days to prove that any of the technology or techniques that we develop in the lab were useful to answer a question. So after that, the compromise was that we will work together in searching for deeper funding that enable us to do a more stable collaboration. And I'm happy to tell that the model is nice, works, and we succeed in a first row in the Imaging for All, in the Academia Latinoamericana de Ciencia, Unión Biolac, Company of Biology. And so far, I will say that I believe or I can see some sustainability of that after Chan Zuckerberg, because now we can regenerate for more funding and make a new call for this first experience and going again to the system and searching for extra funding. So I see there an opportunity for us without basically having to compromise money from our institution, which is for a country like Uruguay very difficult.
Thank you. Yeah, well, we can also remember that there are the LABI programs to access facilities in the whole region, so that's also something to keep in mind. Another question from the audience?
Yeah, for Leonel. Great talk, Leonel. A question on... If I have understood correctly, you are constructing the fifth diver microscope.
You are what, sorry?
Constructing, you are
yes,
making
yes,
the
yes,
fifth
yes,
diver microscope. It looks amazing, 2 photons, 3 photons, so really amazing. What I am, but this is the fifth, I suppose, prototype. So still, what is missing, or what is the reason why it is a prototype? I mean, why? Which parts are not yet for commercial?
One of the things that it always surprised me how the industry developed. Basically, as far as I concern, and speaking with head of the products in companies and things like that, I mean, you have to go to the companies and say, this is a fantastic microscope. You have to pitch here, you have to publish data, you have to collaborate with many people until a company get interested in a prototype and spend 5-10 years in engineering the microscope in order to make a business of it. I believe now for diver it's too late, because the patent from diver is already 10 years old. So basically, there will not be any company interested in pursuing an engineering that will basically give you a few years of revenues. So we are now establishing a startup in Uruguay, developing diver as a technology, not for the diver per se, but rather for the application of diver to clinics. So I don't have a straight answer, Jose Maria, unfortunately.
No, it's a very good answer.
But unfortunately, I see many great technologies here and there that if you are not the kind of person, and Enrico Graton, the person who developed this technology, never was a person pursuing, basically the technology for the purpose of commercializing. He was always open to share with anybody the technology, but not for the business perspective. And I knew that they have the chance to develop this diver with ISS 10 years ago, something like that. They didn't succeed with raising funding for prototyping and engineering, and it never happened. So a fantastic microscope. I completely convinced this is a fantastic microscope. There is no other 2-photon microscope with the capabilities that diver can perform. Will never be commercialized.
Thank you.
Can I comment on this? I would like to comment on this as well, because I went through this myself as a scientist who made a company. And I think most of the scientists, and I speak from myself, lack a proper understanding of what it means to bring a scientific invention, a prototype, to a product. So I had my PhD finished, the prototype was ready, and I thought, great, we have a product, let's make a company. But the step from having a paper published or a prototype ready to have a product is gigantic. Yeah. This is not just the next step and then you're done. It took us years. You have to get the financing in place. You have to, especially when you go into clinics, all the quality management and regulatory aspects need to be met. Yeah. A paper is nice, but it's not enough. No one will give you a certificate to use this technology in a clinical setup for clinical tests or implementation studies, which might cost hundreds of thousands, euro, US dollar, whatever, or even millions, and take many years. But this you don't need to do if you want to stay in research. But then the research market is much smaller, and companies might be less interested in picking this up than when they know they have something which they can sell to potentially every hospital. It's a very like walking through the desert, I would say.
Yeah, thank you very much, Rupert. The last one, last comment.
No, is that this opened. I also started the company 15 years ago, and it went all the way through the normal internationalization and selling. But at some time, it would be interesting to know which is the venture capital market in South America. It would be very interesting to know. I have no idea. I know a little bit, and in Spain it was not so easy. So
thank you very much for that insight from industry. It's always good to know the different sides, right? So we're running out of time. Thank you very much for this amazing session, and we can continue the discussion in the coffee break.